Hello, good morning. My part in our report about heat exchangers will include plate type heat exchangers and shell and tube type heat exchangers. We will start with plate heat exchangers. We will start first with the definition. A heat exchanger is made of stacked four-corner bored metal plates. Each metal plate has holes in its corners, and each metal plate is aligned, creating a virtual tunnel or manifold. Each metal plate acts as a channel for flow because each channel has a rubber gasket restricting flow over the plate face. Heat transfer occurs with the flow of cold and hot fluid in odd and even channels over the front and back plate surfaces. The thin metal plate, through convection and conduction, transfers heat from the hot fluid to the cooling fluid. The heat transfer coefficient in a plate type heat exchanger is increased by the use of chevron corrugations, creating turbulent flow and preventing the formation of a thick boundary layer which would impede heat transfer. Here we have an image of a plate heat exchanger, its assembly and what parts it has. And again, to clarify, a plate heat exchanger is a dense heat exchanger because it uses thin metal plates stacked together to create a heat exchanger with a large surface area because there are many thin plates instead of one thick plate. And again, the way it works is that water or cooling fluids and hot fluids will flow through their respective channels down or up the faces of their assigned plates because it flows in odd and even channels, and they exchange heat indirectly by exchanging heat through convection and then conduction, passing the heat to the metal plate from one side to another. Here we have the energy analysis of a plate type heat exchanger. A plate type heat exchanger uses rubber gaskets so that fluids flow only in their designated channels, because a plate type heat exchanger does not use tubes like a shell and tube heat exchanger. And here we have a video showing the working principle and live animation or demonstration of how it works. In this slide, we have the energy analysis continuation for a plate type heat exchanger. Here in this slide, we have the different formulas taken from our web source Apale with their specific notation for basic or general heat exchanger heat transfer formulas, with a legend for the different symbols on the side explaining what these symbols or what their notation means. In the next slide, we have a continuation of Apale. It is a company that produces heat exchangers, and we have a continuation of their specific notation for general heat exchange formulas, where it is shown here the formula used to get the overall heat transfer coefficient, and to its side the different factors, different coefficients, and different variables and what they mean. Plate heat exchangers also have standards. Standards are generally split into safety and performance standards. ARI standard 400 is a liquid-to-liquid heat exchanger standard meant for performance. What it is: this is the gold standard for commercial and industrial plate heat exchangers, mostly gasketed. If a unit is ARI certified, it means a third party has tested the manufacturer's software and units to prove they are accurate. If a manufacturer says a unit will move 1 million British thermal units per hour with a 5 psi pressure drop, and ARI certification guarantees it will actually do that. And a tip: always ask if the selection is ARI 400 certified. If it is not, you may need to add a safety margin, extra surface area, to account for potential underperformance. The next kind of standard for a plate type heat exchanger is a safety standard, and we have cited UL 207 for this kind of standard. What is UL 207? It is specific to brazed plate heat exchangers (BPHE) used in refrigeration and HVAC. This matters because this tests for fatigue failure, repeatedly turning the compressor on and off. A unit might pass a one-time burst test as per ASME standards, but it may fail after 10,000 cycles of thermal expansion. UL 207 certifies it can handle the rigorous fatigue of a refrigeration cycle. So, although used in refrigeration, this standard is still meant for a plate heat exchanger, a braze type, and it shows that if certified under this standard, a plate heat exchanger would be able to operate in real conditions, not only ideal testing conditions. And now we will show a research or a study using a plate type heat exchanger. This study came from Russia, and the gist of this study is that in a plate type heat exchanger, the usual coolant is water. What these scientists or researchers wanted to find out is, what if they introduced nanoparticles or very minute amount of particles in the water to attempt to change its thermal or heat conduction or ability to cool down the selected hot fluid in the plate heat exchanger. As can be detailed or read here more from the abstract, they did this by adding trace amounts of aluminum and found that even with only small amounts of metals in the water, it significantly changed and improved the heat transfer of water. So this is the future of plate type heat exchangers, because research is going in the direction of not changing the geometry or configuration of the heat exchanger, but changing the composition of the fluids and the common working fluid, water, going into the plate heat exchanger. And here we have a sample problem. The problem says a food processing plant needs to cool down pasteurized water using a plate heat exchanger. We are to find Q, LMTD, and A for area. The solution is on the right side. We are given the change in temperature for the hot fluid is 75 to 50. The change in temperature for the cold fluid is 35 to 55. The overall heat transfer coefficient is 1800 kcal per hour times meter squared times Celsius, and the CP is 1 kcal over kilogram times Celsius. And the formulas used here are Q, LMTD, and we find the area by manipulating the formula for Q. The Q formula manipulated to find for area is Q is equal to U times A times LMTD, and by putting U and LMTD as the denominator of Q, we can isolate A and that's how we arrive to these answers. The answers are: the heat needed to cool down our hot fluid is 3 million kcal per hour. The LMTD in a countercurrent flow plate heat exchanger is 17.38 Celsius, and the area required, the total surface area required for this plate heat exchanger would be 95.89 meters squared. And although that is a substantial area, the benefit of a plate heat exchanger is that by stacking together multiple thin plates, this kind of area is achievable with a small volume heat exchanger, because heat transfer depends primarily on surface area, and an increase in thickness of a material increases thermal resistance. That is why thin metal plates are used to, let us say, gimmick physics to get better heat transfer, because there's less thickness, less thermal resistance, at the same time giving our fluids more area to transfer their thermal energy to. So that ends our report for plate type exchangers. Continuing, we will now report on shell and tube heat exchangers. The definition first. A shell and tube heat exchanger, or exchangers like plate heat exchangers, transfer heat through convection and conduction through indirect contact. Shell and tube heat exchangers use pipe or tube configurations either in horizontal or vertical position, where one fluid is in the shell and the other is in the tube. Compared to plate type heat exchangers, they are not as dense, take up more space, but have less severe pressure drops and require less pump work, because the flow is not as turbulent in the tube, but it may be in the shell. This was not addressed before, but since a plate type heat exchanger does not have tubes flowing through its channels, what it has instead is an alignment of holes on the corners of the plates that act as a virtual tunnel, a manifold, where the water or the fluids, hot and cold, are pumped through it, and they flow up or down. Usually the cooling fluid flows up and the heating fluid goes down over the faces of the thin metal plates, and this flow is separated or prevented from mixing by rubber gaskets, so that heating and cooling fluids only flow on their designated odd or even channels. This requires that the plates are perfectly aligned, that the rubber gaskets function, and because of this, it creates turbulence, because the water or the working fluids do not flow through a smooth tube, so the flow is not turbulent, the flow is not laminar, and because the flow is turbulent, it erases or it reduces the effect of a boundary layer that acts as a thermal insulator, preventing proper thermal conduction. Because if flow is turbulent, fluid particles cannot settle and create this boundary layer, because the fluid is turbulent, because it has no tunnel that is physical, it goes through a virtual tunnel, and also because the nature of a plate type heat exchanger is that it requires more pump work, because it's similar to the problem of the chicken and egg, where one thing precedes another, but in a plate type heat exchanger, all of these are true all at once. There is no pipe, there is no pipe, they rely on perfectly aligned plates, there's only a virtual tunnel and manifold, the fluids flow down or up the plate surfaces, the faces of the thin metal plates. The flow is turbulent because of this, and the flow is also turbulent because the pump work required to move fluid through this configuration is high, and also because that pump work is high, the flow is turbulent. It would make more sense or it will make more sense upon a few more reviewings of the attached video on how a plate type heat exchanger works. One area of confusion typically is how can it be that the cooling fluid flows up? Usually, a cooling fluid flows down because of gravity, but this is because the pump work exerted in a plate heat exchanger system is greater than the effects of gravity. So, a cooling fluid is forced up, similar to how the pressure in a hose forces water up even if the hose were to be oriented upwards. And again, because of how much work is exerted, the flow is turbulent. And because this flow is turbulent, the work to be exerted is high. And at the same time, because it has to be this way, the flow has to be turbulent, or rather, because it has to be this way, the pump work has to be high, therefore the flow is turbulent. There are certain or many conditions for a plate type heat exchanger to work that words would not do justice unless written on paper, but they are true concurrently. And that is the advantage of a plate type heat exchanger. They are dense, they are effective, they are efficient, but the downside is they require greater electrical input because their pumps have to work harder. Now going to shell and tube heat exchangers. Compared to plate type heat exchangers, they are not as dense, they take up more space, but they have less severe pressure drops and require less pump work because the flow is not as turbulent in the tube, but it may be in the shell. Here we have a diagram of a shell and tube heat exchanger, its different parts and how it is assembled. And here we have a shell and tube heat exchanger, a kind of energy analysis showing how the fluids flow and how heat is exchanged. And here we have a video showing how this works.
Shell and tube heat exchangers will look something like this. With this design, we normally find the inlet and the outlet for one fluid at the very end of the heat exchanger, known as the header. Then we have another inlet and outlet for fluid 2 on the main body, known as the shell. Inside the unit, we have the tubes. These bend and loop around to start and finish at the tube plate, which sits between the shell and the header. The tubes will usually also pass through some baffles, which are sheets of metal. We will see how these work in just a moment. The header, as well as the tubes, can be removed for cleaning, repairs, and maintenance. Inside the header is a sheet of metal known as the divider, or the partition. This separates the tube ends, enabling the fluid to flow into and then out of the heat exchanger tubes. Fluid 1 will flow through the header, into and around the tubes, then back to the header. Fluid 2 will enter the shell and surround the outside of the tubes. The baffles will partially block the flow, which will force the fluid to turn multiple times. This creates a turbulent flow and ensures that fluid 2 mixes with itself, which ensures maximum heat transfer. For example, we might find this in a pharmaceutical factory with a boiler providing steam into the shell, which surrounds the tubes. A chemical product is then pumped through the tubes, and this absorbs the heat of the steam through the tube wall. So this product is going to exit the heat exchanger much warmer. Meanwhile, the steam will start to condense into a liquid and flow back to the boiler to...
After the video, we continue with the energy analysis portion of the shell and tube heat exchanger report. From our web source, we have typical formulas used and the meaning of the different variables used in the formulas. And continuing, like plate type heat exchangers, here we have the standards used. The first standard is the ASME Boiler and Pressure Vessel Code, Section 8, Division 1. What this does? This is the legal requirement in most countries compliant with the ASME code. It treats the heat exchanger as a pressure vessel to ensure it does not explode. The key focus: wall thickness calculations, welding quality and inspection, and pressure testing or hydro test rules. Second standard. Standards of the Tubular Exchange Manufacturers Association. What this does? While the ASME code handles safety, TIMA, or Tubular Exchanger Manufacturers Association code, handles the functionality and fabrication. It defines specific terminology like type BEM or type AES and tolerances. Key focus. It has three classes. These classes, it divides exchangers into three classes based on severity. Class R, refinery, heavy duty, harshest conditions. Class C, commercial, general industrial use. Class B, chemical process service. Clearances, how much space must exist between tubes and baffles. Baffle cuts, standard shapes for directing flow. And here we have a study using a plate type. Here we have a study using a shell and tube type heat exchanger. This study was performed in Pakistan, and the purpose of this study was to find out what shape would be best for heat transfer or heat conduction coefficient, in short, heat transfer, in a shell and tube type heat exchanger. Typically, we use smooth tubes, and because of that, the fluid in those tubes has laminar flow, and the fluid in the shell has also a near laminar transitional or rarely turbulent flow, depending on the volume flow rate and how hard the pump is working. The gist of this study is that they found, instead of a smooth round tube in the shell, heat transfer was better when instead they used hexagonal tubes in the shell. Unlike plate type heat exchangers, where research is in a direction of changing the fluid composition going in, research in shell and tube heat exchangers seems to be taking the direction of changing the tube geometry inside the shell. Not that research in this type of heat exchanger cannot also include changing the composition of the fluids flowing in the heat exchanger, but because the fluids have pipes and tubes that they travel through, and because they're not like plate type heat exchangers where they travel through only a virtual tunnel, the geometry of a shell and tube heat exchanger is more important to consider first. Now, lastly, we have the sample problem for shell and tube type heat exchanger, taken from the same online source where we got our formulas from. Here, we are told to estimate the heat exchanger area needed to cool 50,000 pounds per hour of a light oil. Specific heat is given from 190 degrees Fahrenheit to 140 degrees Fahrenheit using cooling water that is available at 50 degrees Fahrenheit. Below, we are given a diagram, and the solution is, first we must calculate the required heat transfer rate, and because the problem is imperial, we convert units, or if the units, yes, my mistake, the units are already given an imperial, so we continue. Unlike the plate type heat exchanger problem, the units were metric. So the first step is to calculate the required heat transfer rate, and the second step is to calculate the log mean temperature difference. Once we have those, we can now get the preliminary area estimate of the heat exchanger using the same manipulated formula as previously. Area is equal to Q over U times LMTD, but their notation for LMTD here is T subscript M, and from here we get 178.7 feet squared. And we can also get the required mass flow rate of water from the following equation. Q is equal to M times Cp times change in T subscript M. Rearranging that, since we have Q, since we have Cp, and since we have change in Tm, we get 28.978 pound per hour mass flow rate. And that ends my part of the report for heat exchangers.
So, good day everyone. My name is Jose Martin Carias, and my topic is all about double pipe heat exchanger. So, first, ato sang ila-ilahon kung saan yung double pipe heat exchanger. So, a double pipe heat exchanger is the simplest type of heat exchanger. It consists of two concentric pipes, one inside the other. One fluid flow inside the inner pipe, the tube, while the other fluid flows in the annular space between the pipe. So, ang isa ka inner pipe is ano siya mo silbi ba murag mo daloy ang iyahang fluid or ani siya mo agi. Then ang annular space pod is kanabitang sa duha ka tube ani siya mo agi ang ikaduha nga kanabitang ani mo flow ang ikaduha nga fluid. Then key characteristic is simple design, easy to clean and maintain, then suitable for small heat duties, and can be arranged in series or parallel, then commonly operates in contraflow or highest efficiency. So ang kuan ani is wala dali ra siya ang design, then dali ra pud siya mahinduan ug ma-maintain mo na iyang mga key characteristic. Then ihang so dali ra kayo siya sabton, mas kasagaran jud is common siya nga gigamit sa mga gagmay nga industry o kay itong gagmay nga cooling or heating operation. So mga application niya is oil cooling or heating, waste heat recovery in small system, then chemical process industries o cooling engine lubricant, hydraulic oil. Then ari na po ta sa iyang energy balance heat transfer. So ang iyang mga mo ni iyang mga equation or mga equation niya ba sa heat transfer. So familiar naman ta kasagaran ano kay ning labay naman ta heat transfer pag third year. So mo na Q hot and Q cold is equals to Q cold. Kuan ra ba maklaro ra ba. Then MCP, then sa hot na siyang kuan belong, then T hat in minus T hat out. So kasagaran is Q MCP is equals to delta T or T in minus T out. Then equal po na siya sa MCP nga kanang si tawag na cold T out minus T in na pod mo na equal Q hot and Q cold, so equal na sila. Then napot gitawag nga overall heat transfer coefficient mo na gitawag nga Q is equals to UA delta T. So U is overall heat transfer coefficient mo nagiyang unit watts per meter squared Kelvin. Then A is obviously heat transfer area. Then delta T lag mean temperature difference. So mo na no ay nakabutang na sa lagming temperature difference or LMTD contraflow has a higher LMTD or kanang mas kuan siya sa better efficiency. So ano na may buwan na to ang nanay nakabutang na overall heat transfer coefficient. So ari ta siyang mga kuan standard use in testing. By the way, atong ibalik ang isa ka slide. So kana din kuan kaning mga equation or kaning gigamit nga formula nga QMCP delta T or manat T in means T out. Ani jud murag silbing ani tama kay ba kung unsaon pag-analyze o pag-compute sa heat exchanger kana. Wala siya. Pero mostly nakaibaw na tang tanan kay nakalabay na ta heat transfer. Then Aritas standard use and testing. Although double pipe heat exchanger are simple, the following industry standard may apply. Mana as may boiler and pressure vessel code. For design of pressurized piping and vessels, then ensure safety during operation. Then dapat ay team standard or tubular exchanger manufacturers association. Muna defines mechanical design and testing or covers material selection, inspection and performance. Then nato is the material standard, ensure pipe and metal compatibility. Then um nato example is the A106 or carbon steel pipe. Then napot is the A312 stainless pipe. Then ISO 14001 or ISO 50001 for evaluating thermodynamic performance and energy efficiency. So unsa ni standard use and testing di. So kani siya nga atong gisiguro ani ang murag silbing iya bitong efficiency gali so kaligtasan bitaw or kalidad sa mga material nga atong gigamit ya. So masabtan naman siguro po no ang ato ang pasabot ani. Then natay sample study research findings. So study 1 increasing heat transfer by turbulators. Adding twisted tape inside the inner tube increase heat transfer up to 40 to 60%. So, kinahanglan ta magbuta og twisted tape sa sud sa tubo para makakuan ba makataas ta og heat transfer mga 40 to 60%. Pero mutaas po diya hang pressure ko no, pressure drop increase need more pumping power. So kinahanglan po ta taas nga pump. Then study to effect of flow arrangement. Contraflow configuration show 20 to 30% higher thermal effectiveness than parallel flow, then recommended for industrial use. So, ang iyang contraflow ko na is 20 to 30%. Mas epektibo siya kaysa sa parallel flow. Then, nanofluid improvement is using Al2 or oxygen 3 the water nanofluid improve heat transfer by 8 to 15%. So based for kung application is siya. So muna na paggamit ato og taas sa heat transfer po. So kani siya is nindot kayo gipakita ni nga nindot kayo jud ang performance sa heat exchanger. So ari na ta sa sample problem. Hot oil enters a double pipe at 120 Celsius, degrees Celsius and leaves at 80 degrees Celsius. Cold water enters at 25 degrees Celsius and leaves at 60 degrees Celsius. Water flow rate 1.2 kilogram per second. Then heat transfer rate. So sa yon ra kayo no? Nata equation, pwede na lang nato na i-substitute sa mga value. Then makakuha na ta sa answer. Then same sa problem 2, pero kani siya overall heat transfer coefficient na yung gigamit ani required niya is area man ang pangita. So sa pag-analyze po sa problem mahibaw-an po nato sa mga given no ug unsay atong gamiton nga formula. Then ano ta makam ako kay kanina nga formula atong gamiton kay so far isa ning heat transfer sa kinadaghanan jud formula po sa mechanical engineering nga course. So arin na tas conclusion no. The double pipe heat exchanger is a simple yet effective device for transferring heat between two fluids. It is straightforward design, ease of maintenance, and suitability for small scale operation make it a reliable choice in many industries. Analyzed through energy balance, LMTD, and performance equation allows accurate design and evaluation. Research shows that the performance can be significantly improved through enhanced fluid turbulence and optimized fluid arrangement. So mo na siya no ang atong ang sabtan po nato nga ang double pipe heat exchangers jud is simple siya pero epektibo. Then kinahanglan po nato mo analyze ta sa paggamit sa energy balance ug sa LMTD. Then mas tindot pud ang iyang performance ug mogamit ang autoregulators, the no fluid o water flow arrangement. Mm, so far unta nasabtan ninyo ato ang topic o maura to dang salamat and good day again once again.
Spiral heat exchangers. Introduction. Spiral heat exchangers are compact devices used for heat transfer, designed with two wound metal plates forming spiral channels, effective for viscous and falling fluids. So the spiral heat exchangers is a compact and efficient type of heat exchangers commonly used in industries that require reliable heat transfer. Ang idea niya kay dali ra siya i-clean, high efficiency o gamay rag space. Mao ni siya ang gipili sa daghang planta kay stable iyang performance. Bisag taas og temperature or dirty ang fluids. In engineering practice, gigamit ni siya kung gusto nato og steady heat recovery while minimizing energy loss. So let's proceed sa definition. A spiral heat exchangers or SHE is consist of two metal stripes wood into spiral, creates two separate channels for counterflow heat transfer. So, a spiral heat exchanger is a device that transfer heat between two fluids using two spiral-shaped channels rolled around the central core. And then, ang layout niya kay twist or spiral form para taas ang surface area, meaning mas daghan og contact between hot and cold fluid. Mao na kusog iyang heat transfer rate. Usually ang usa ka fluid moagi sa usa ka spiral channel. Unya ang precast fluid sa opposite channel separated by metal plates to prevent mixing. So we'll proceed to next slide. History and development. Introduced in the mid-20th century for high fouling industries. Improved through advancement in welding and plate forming technologies. This type of heat exchanger was developed around the 1930s when engineers were looking for more compact and self-cleaning design. Sa kadugayan, nakita nila nga ang spiral arrangement kay effective sa pagkontrol sa fouling kanang build up sa dirt. Daghan kayo improvements karon like mas lig-on nga materials, better sealing methods ug mas precise nga fabrication. Industries later adopted spiral designs tungod kay proven siya nga long-lasting, less prone clogging or high efficiency sa heat transfer. So now, let's proceed to construction components. Introduced in mid-20th century, our spiral plates, channel spacers, end covers, inlet and outlet nozzles. A spiral heat exchanger is mainly made of two metal plates rolled into spiral. These plates create two isolated flow paths, cover plates or both ends, seals or gaskets, o connections para sa inlet and outlet. Ang plate thickness depends on pressure rating. Kung high pressure, mas baga. Ang mga components kay spiral plates, mao ang main surface for heat transfer, spacer studs para dili magdikit ang plates o para ma-uniform ang spacing, end covers para sa seal ang two channels, connections or nozzles, inlet ug outlet sa fluids, gaskets or welds mo separate sa duha ka fluid. Simple ra siya tanawon pero engineering wise critical ang spacing ug uniformity kay maoy mo determine sa performance. So mo proceed na sad ta sa working principle. Hot and cold fluids enter separate spiral channels. Counter current flow arrangement maximize heat transfer. Self-cleaning effect due to uniform velocity. The two fluids enter separately into each spiral channel. One fluid in a spiral inward path, while ang PCAS kay outward or vice versa. As the fluids travel in opposite directions or counterflow, mas effective ang heat transfer. Ang setup niya kay force convection tungod sa narrow spiral channels. So, kusog ang turbulence. Mas maayo ang heat exchange, heat flows through the metal plate, separating the fluids. Ang unique feature niya kay self-cleaning. Kung ang fluid medyo hugaw, kay naay high velocity zones nga mopush sa dirt outward. So, let's proceed to next slide. Types of spiral heat exchangers. We have 3. Type 1, both fluid single pass. Type 2, one fluid multipass. Type 3, condensing and evaporating type. Spiral for liquid to liquid, both fluids are liquids, common in chemical plants. Sa spiral for condensation, hot vapor condenses while cold water absorbs the heat. Sa type 3, used for evaporation processes. Sa akong nakita, ang type selection depende sa process requirement. For example, kung dirty service like wastewater, mas preferred ang liquid to liquid spiral kay strong og easy to clean. And then next, energy balance and LMTD. General equation, Q equals U times A times delta T Lm, where Q is heat transfer rate, U is overall heat transfer coefficient, A is area, delta T Lm lag mean temperature difference. So in analyzing heat exchangers, we use energy balance, heat lost by hot fluid, heat gained by cold fluid. Since heat exchangers often operate in counterflow, we use mean temperature difference or LMTD formula to calculate the effective temperature driving force. Ang counterflow arrangement kay mas taas og LMTD compared sa parallel flow, meaning mas efficient. The spiral geometry also maintains uniform temperature gradient along the path, which improve overall heat transfer. And then let's proceed to applications. Wastewater and sludge treatment, food processing, chemical and petrochemical, pulp and paper, heat recovery units. So sa spiral heat exchangers are widely used in chemical processing, food industries, petroleum refining, wastewater treatment, and power plants. Sa wastewater, grabe sila ka useful kay makahandle og dirty fluids. Sa food industry, ginagamit for heating or cooling liquids like juices or dairy. Sa chemical industry, helpful kaayo sila for recovering waste heat, makatabang og save sa energy cost. So next slide, dire na sad ta sa advantages. Advantages, compact and efficient, handles dirty fluids, high heat transfer coefficient, and easy maintenance. So, ang advantage nila, some strong advantages include compact size, high heat transfer efficiency, ug self-cleaning capability. Dili ra siya dali maklag, mao na preferred siya sa plants dealing with slurries and viscous fluids. It also has low pressure drop due to smooth flow path. Ang setup kay easy maintenance and long life og stable performance maski mag-long operation. So dara na sad ta sa next slides. Which is ang iyahang counter side, which is ang disadvantages. Not suitable for very high pressures, higher fabrication cost, and limited plate thickness. Ang disadvantages niyo kay ang limitations kay sensitive siya sa improper sealing. If dili tarong ang gasket or welds, dali ra siya mag-leak. And also another disadvantages is dili siya ideal for high pressure gas to gas applications. Costly pod siya, mahal ang fabrication kay specialized forming process. And once mabungkag nimo ang end covers, medyo lisod ipuli ang exact original seal unless trained ka. So, next in this slide no, natay ipakita na video o how the spiral heat exchangers works. So, atong tanawon.
Spiral heat exchangers look something like this. We have a flanged inlet on the front face, with the outlet located on the top. Then we have an inlet from another fluid, also on the top, with the outlet located on the rear face. Behind the end plates, we find two sheets of metal inside, which spiral together around the interior to form a channel which the fluids will now flow through. The channel completely separates the two fluids. We see the first fluid enters the heat exchanger and fills the chamber, then flows around the channel and to the outlet. Meanwhile, on the other side, the second fluid is entering via the top, flowing around the channel and into the chamber, where it then exits. The two fluids enter and exit at different temperatures. This type of heat exchanger isn't as commonly used. However, because the design has only one channel for the fluid to flow through, the velocity remains high, making it harder for fouling to occur, whereas plate and even tube heat exchangers divide the flow into multiple paths. So these are ideal for installations where sludge-like substances are processed. For example, in an anaerobic digester, where the thick sludge is recirculated through a spiral heat exchanger to maintain a certain temperature. This releases methane from the digester to power an engine and then turn an electrical generator. Check out one of these videos to continue learning about mechanical and thermal engineering, as this is the end of the video. Don't forget to follow us on Facebook, LinkedIn, Twitter, Instagram, TikTok, as well as theengineeringmindset.com.
Hello everyone. Here to report topic 3, which is regenerative heat exchanger. So what is regenerative heat exchanger? A regenerative heat exchanger or regenerator transfer heat between two fluids by intermittent storing heat in the storage medium, such as a matrix. It works in cycle. A hot fluid heat the storage medium and then cold fluid absorb the stored heat from the medium. Before the cycle repeats, with a hot fluid reheating the medium again. This process improves energy efficiency, especially in applications like gas turbine engine, power station, and metallurgical industries, by preheating the fluids before additionally processing. So, how it's work? Cycle 1, the hot fluid flow through the heat exchanger matrix, transferring its thermal energy to the storage material and heating it up. Cycle 2 is the flow of the hot fluid is stopped. The cold fluid then flows through the same matrix, absorbing the heat that was stored there during the hot cycle. Cycle 3, which is continuous operation. For continuous operation, regenerative heat exchanger typically use a pair of matrices, while one is in the cold flow phase and the other is hot flow phase. So key characteristic cycle operation. Like other heat exchanger, where fluids flow continuously, regenerative heat exchanger operates in cycle. Its storage, they use the thermal storage medium to temporarily hold heat. Potential for mixing, there can be a small amount of mixing between the hot and the cold fluid, which is an inherent disadvantage of this type of heat exchanger. Last is application. They are commonly used to improve efficiency by preheating fluid in applications like gas turbine engine, power station, and furnace. So we proceed to the energy balance. The energy balance equation for the regenerative heat exchanger under steady-state steady flow condition is an application of the first law of thermodynamics for open systems, primarily focused on a net exchange and the fluid stream. The general principle is that the rate of the energy entering the system equals the rate of energy leaving it, with the heat transfer between the hot and cold fluid between the primary energy exchange mechanism. General steady flow energy equation. For the control volume like heat exchanger, and assuming negligible changes in kinetic and potential energy, no work interaction, no pump or turbines within the control volume, and an adiabatic system boundary, no heat loss to the surroundings. The general energy balance equation simply signifies Q minus W plus summation of M times H equals to summation out M times H plus PE over dt. The Q is heat transfer, W is net rate of work done, M is mass flow rate, H is specific enthalpy, dE over dt is the change of energy within the control volume, which is zero for steady state. Regenerative heat exchanger energy balance. In regenerative heat exchanger, heat is transferred internally between the hot and cold fluid. For ideal adiabatic regeneration and steady state, heat loss by the hot fluid is internally within the cold fluid. Then energy balance can be broken down for the hot and cold during prepare. For the hot fluids, the heat loss is Q equals to N times Cp times Tn minus T out. For the cold fluid stream, the heat gain Q equals to N Cp times Tn minus T out. Overall equation, assuming no heat loss to the surrounding and steady operation, the heat transfer from hot fluid is equal to heat absorbed by the cold fluid. So QH equals to QC. So we convert to N times Cp Tn minus T out equals to NC Cp times Tn minus Ti. This energy balance equation allows you to calculate the nominal flow rate or temperature and other parameters are known. Standard use in testing generative heat exchanger. Testing of the regenerative heat exchanger often fall under broader industry standard for pressure vessel, heat recovery, and general performance testing rather than specific universal generative heat exchanger testing standard. Key standard of organization involved include ASME boiler and pressure vessel code, primarily Section 8 for design and manufacturing vessel pressure vessel, and Section 5 for non-destructive testing of friction procedures. Next is APE standard specific to the oil, gas, and petrochemical industries. APA 660 covers shell and tube heat exchanger, and API 566 fired heater and air heater, which often employ regenerative heater. ISO standards and International Organization for Standardization provide general quality and performance standards. ISO 16494 specifies test methods for performance metrics of heat recovery, ventilation, and energy recovery ventilation. ISO 9001 relates to generally quality management system for manufacturing. Next is ASTM standard. These cover material properties and specific test method. Example include standard for material segregation of tube and measuring thermal conductivity. ASHRAE standards, the American Society of Heating, Refrigerating, and Air Conditioning Engineers state standard for HVAC application, including energy conservation measurement and heat recovery ventilation system. Sample study of research and findings. A common area of research involved using generative heat exchanger to improve the thermal efficiency of gas turbine and waste heat recovery system for ventilation. First research is the performance of regenerative gas turbine power plant. based on findings in the study of SCIRP open access and related research. Objective of the study is to analyze how the addition of the regenerator and its effectiveness influence the performance of the gas turbine power plant cycle under various operating conditions. Methodologies to study utilize thermodynamics modeling and simulation software to conduct a parametric analysis of the gas turbine cycle with or without a generator. The model were used to calculate properties at various state points of the cycle. Key findings of the research is increased thermal efficiency, adding regeneration to the simple gas turbine cycle significantly increase the thermal efficiency. This because of the compressed air entering the combustor is preheated by waste exhaust heat, reducing the amount of fuel required. Impact of effectiveness increase the limited effectiveness, the measure of how closely the outlet temperature approach each other. Directly result in a higher cycle thermal efficiency and increase output power. Third is optimum pressure ratio peak. Regenerative cycle often achieve peak effectiveness lower optimum pressure ratio compared to simple cycle, making them more feasible with current compressor technologies. Reduce exhaust temperature. The use of the generator leads to decrease the exhaust gas temperature as more energy is covered internally by the system. Next study is comparison of generator units for efficiency. The study investigates how minor changes in physical arrangement of the heat storage material can affect overall performance. The objective is to investigate the effect of three different various mesh agreements on the thermal efficiency of the pressure drop of the regenerator using computational fluids dynamics simulation. Methodology is the research approves CFD methods to compare the performance in the line and staggered regenerator, keeping constant other constant. Key findings the inline generator increased average efficiency by up to 3.6% compared to the staggered design. The inline arrangement also showed a lower average pressure drop, around 36 QA lower. The optimal geometry depends on the specific operating condition defined by the reduced length parameters. Inline generators are generally recommended for shorter wavelength, while staggered design may be better for larger ones. Paying attention to the correct choice of regenerator geometry is a critical factor in maximizing performance of reducing of the original cost. Last is advanced generator using phase change material. The recent area of research involved integrating phase change materials into the regenerator matrix to improve energy storage capabilities. The objective is to propose an analysis novel regenerative heat exchanger using custodied PSNS to address issue with temperature swing. A thermodynamics model was developed to compare the performance of regenerator with latent heat storage matrix versus standard sensible heat storage matrix. Key findings is the LRAPX can obtain a relatively more uniform outlet fluid temperature which is highly beneficial for consistent pressure control. A large efficiency improvement was observed using cascade PSNS. This approach is promising alternative for solving a problem caused by temperature swing common in regional refrigerator, making the system more stable and efficient, especially at lower rotation speed. I have a sample problem of united heat exchanger which is a rotary regenerative heat exchanger. The rotary generator is used to cover heat from hot to gas or preheat fresh air in the industry process. The system operates on steady state with measurable heat loss to the environment. Given hot gas flow, M is 5 ks, 5 kg, S T in is 300 Celsius, T out is 1000 or 150 Celsius, Cp is 1.05 kj over kg times consume constant. Cold air fresh M also MPJ is EC EC in is 30 Celsius, CPC is 1.01 assume constant. Find EC out. Solution is Q Q equals to QTC MHCPH times T in minus T out equal to MCCPC times T in T out minus T in. Find first the Q, the hot gas, which is MHCPH times T in minus T out. Substitute 5 times 1.05 times 300 minus 150 Celsius. The answer is 787.5 kilowatts. Next is find the T out of the cold gas, cold air. Formula is Q equals MC CPC times D out minus D in. Transpose the temperature T out minus D in equals to Q over MC CP, and transfer the T in to the side, which can get TC out equals to TC in plus Q over MC CPC. Substitute the values so we can get TC out equals to 225 Celsius. So that's all.